Hello, everybody. Thanks for joining us today, and welcome to the Qimera Automated Correction of Refraction Residuals webinar. I'm Samantha Bruce, QPS Technical Sales Engineer, and I'll be acting in a support role today, setting the stage for the webinar and helping to answer questions in the background. Also online, we have Jonathan Bodwin, the Qimera Product Manager, who will be the primary presenter for today's webinar. Following our usual format, we'll use some slides, but the focus will largely be on demoing the software and answering any questions that you may have. So if you do have a question during the webinar, please just type it into the chat box, and I'll be monitoring that chat box and I'll provide some answers directly in there. And otherwise, we'll pause and answer questions out loud. Some other info to note, just above the chat box, you'll notice the handout section of GoToWebinar. And there you'll find the Qimera how-to document that explains how to use the TU Delft sound speed inversion tool that we will be covering today. You'll also see the Qimera 1.6 release notes, which discuss the tool, and a few research papers explaining the science behind the tool. Last thing I'd like to mention is that QPS does offer free software evaluations. And you can request a software for a free evaluation anytime by visiting our website. But to streamline the process for folks participating today, if you type evaluate in the comment box during the webinar, I'll follow up with you directly and arrange an evaluation license with you through email. So, and as always, this webinar is being recorded and will be made available on YouTube for future viewing. So that covers the bit of housekeeping I needed to do. And now I'm going to turn it over to Jonathan to begin the feature presentation.
All right, thanks very much, Sam. So what we'll do today is I'll go over a talk that I gave first at the Shallow Survey Conference in St. John's, Newfoundland earlier this year, covering this exact material. And I gave a very similar talk at the Hydro Conference in Sydney, Australia about a month later. I've since just tweaked it a little bit, added a few slides. So if you've been to either of those conferences, it's largely the same talk. What's interesting with the webinar format is we have the chance to have some Q&A with folks. So I'll just dive right in and get started. First, I want to acknowledge the people that worked on this. I get the fun part of showing it off to everyone, but really I did actually very little coding and work. It was the hard work of Weston Renaud, who works with us in the Netherlands office of QPS. He worked very closely with two colleagues at the Technical University of Delft, Tanaz Mohamedlou and Miriam Snellen, the researchers who came up with this approach, and then Tanaz helped us to implement it in Qimera. So they did all of the work, and I'm very proud to show off their work here today. So I'll start setting the stage a little bit, basically with a bit of storytelling, kind of to get people familiar with the problem. We'll start with, just in case everyone's a little unfamiliar, what's sound speed and refraction? The speed of sound changes through the ocean's water depths. Here we have examples, red and green and blue, different measurements of the sound speed through the ocean. And what that does to acoustic rays is it causes them to refract. So if you have an ocean that's behaving like the red sound speed profile, you'll have an acoustic ray path that takes a particular refracted path, and then likewise with the green and the blue. And what's interesting is if you think the ocean's acting green today, for example, in the sound speed profile, but you instead use the blue profile to correct your data, instead of getting a flat C4, you get a smile type artifact. And vice versa, if you think the ocean is acting with the green sound speed profile, but instead you're using the red, you get a frown artifact. And these are the types of problems that we're trying to fix. It's difficult to always measure what the ocean's up to every day. Sometimes you have to measure it quite frequently, sometimes not a lot, and it's a tough problem to solve. So these are tools that we'll be covering today that help you iron these problems out. So we'll start with a personal story of mine working with some colleagues in Halifax, Bedford Basin specifically, to collect the R2Sonic multispectral challenge data set with an R2Sonic 2026. We went out for a few hours, and we had my own personal journey through having refraction errors in a data set that you intend to have use for. And really, it's a bit of a story about the 5 stages of grief that you go through. And so what I'll do is I'll walk through a couple of videos that show this particular journey with the data set that I personally collected, and in the end, how we were able to clean it up. So stage one is denial. I have a little video here, and I'll just narrate over the video. I'm going to try and make it so that I don't lag too behind, because the video doesn't always come through as quickly as we'd like with GoToWebinar. So here we have a data set, and there's obviously it's a general type of artifact. You can see if you profile that there's differences in depth, and it creates this sort of ribboning artifact in the terrain model. What we typically do with this is have a look at the standard deviation. So if we color the surface by the uncertainty and then change the color map to something that we typically use, it's the mid-water color map. And you can see where the soundings from different passes agree with each other. They're in a nice light blue, and where they don't agree with each other, it's in red and green. And if you zoom out, you can see that some areas have general disagreement between successive passes versus others where it's nice and common and they agree well with each other. And so it's one thing to look at a grid. It's always good to look at the soundings that have made the grid up. And so what we'll do here is grab a little slice of the data and load it up in our slice editor, and you'll see all of the different soundings from the different survey line passes. There's maybe 12.5 lines here. And you can see right there that we had that interesting looking terrain model, and now we've confirmed with just looking at the soundings that it's indeed a refraction problem. So you can see that by the soundings on the right having the smile type artifacts. I'm moving my mouse over that. Hopefully that's coming through. And then the soundings on the left, the different color coding between the different survey lines are showing no refraction problem, or a much milder one. So stage 3, we'll skip over stage 2 of anger. So bargaining. We're going through the data set and we're trying to convince ourselves that this is something that we can fix. Well, we must have made a small processing error. So here what we'll do is use Qimera to just quickly scan through the data set and see if we can fix it using the traditional methods of just double checking our work. So here we'll load up all 4 of the sound speed profiles in the sound speed editor. And you can see here that someone will make a vain attempt to clean out a little spike in hopes that that's the cause of the problem. So we'll hit save on this, and you'll see that Qimera links that up to the multibeam files that are actually affected by that. You'll see the little reprocess icon next to the line. So this already is a hint that this is probably not the cause of the problem. You reprocess, hopefully the map gets better, maybe the green and the red goes away. And of course it does not. That was not the problem. And so you've done your usual job. You looked at the sound speed profiles, they make sense. Most surveyors would then look at how they're applying the sound speed profiles to their data. So in this case, you go to Qimera's processing settings editor, and this is where you start to grasp at straws typically. You're trying, maybe if I try nearest in time, or nearest in distance, or nearest in distance within time, and at this point you're trying things until it works. And this is the typical way that people get through this problem, is you're going through and you're trying to find something that just makes the problem go away. I think I skipped a spot. Oh, that's right. So at this point, we zoom in a little bit here. Oh, I think I accidentally repeated a video. Stage 5. So lastly, we've got a refraction problem. We've realized we've double-checked everything, the data, we've double-checked how it's applied. We're finding that we've done all of the right things that we could. At this point, you just accept it and move on. And so in this video, we'll show how the interesting tool that we've built with the Technical University of Delft can be used to fix this kind of problem. So you select the lines, you run the tool. There's a small set of parameters that you choose from. We've tried to choose really intelligent defaults that get most people in the right spot most of the time. And it runs as a background process, and it updates the grid. And what we're hoping to see is that all the greens and reds go to a nice calm blue. And that means the uncertainty between different passes is really beaten down, and there's good agreement between the different passes. And you can see that's indeed the case. So let's talk a little bit about the results. So I grabbed a slice of data. On the lower right-hand side, you'll see the overview map with a red line showing a section, and that's the initial set of points that we demoed in that first video. And that's basically at the top is the before. And after TU Delft running, we get the after. And you see there's really, really nice agreement, as much as we possibly can, between the successive passes and the different survey lines. So let's talk about the algorithm a little bit. This was work that was done by Miriam and others as early as 2009. I think there's an earlier paper as well from 2008 with another co-author. And this was done, like I said, 2009. There was funding available for commercial implementation in 2016. And we partnered with the Technical University of Delft to make that happen. They had the know-how at the algorithm. It was written in MATLAB and other kinds of source code. And we worked with them to convert it into our code base. And we released that exclusively in Qimera 1.6 in February of this year. So let's just go over the quick benefits of the algorithm. I'll get into the details. It's objective, it's automated, it's physics-based, and it's accountable. And so let's just get right into that. Let's start with it's an objective algorithm. So what I'm showing here is how someone might have used a subset view to manually correct refraction problems in Qimera using a refraction correction filter profile. In this case, you select one or more lines and then you apply a refraction corrector at a user-specified depth. In this case, if you look at the top right, at the depth of 1 meter, we apply a sound velocity correction of 1 meter per second. And that becomes a tool that you can apply in the slice editor. And by applying it successively one after another, you can bring the swath into alignment with the neighbors, which is what you see that I've manually done in this small video here. And what's interesting is if you're watching closely, the number of clicks that it took to beat down each particular pass differs from left to right. In one case on the far right, you see it took 11 clicks with that 1 meter per second filter to flatten it, versus on the far left, it took only 1 click, 1 meter per second. So this is the part that's very subjective. There are tools out there to do this that are, I think, largely available in many, many hydrographic processing applications. But they all have this same approach where a user is looking at it and they're clicking a button until it's flat. And then you proceed through the whole data set. And that's the subjective part. Where this algorithm is quite interesting is it's objective. It will give you the same answer, independent of operator, time after time after time. And that's a big advantage in a lot of these types of algorithms in our industry. So let's go to the second benefit. It's automated. I walked you through the painful process in the last slide of showing what it's like to have to manually go through and correct these types of problems. It takes time. It takes a lot of time. It's tedious. It's error prone. The nice thing about this algorithm, if I activate the video in the lower right, just a recap of the one we saw earlier. You select the lines, you run the tool, and it just goes. You don't need to review the data swath by swath, line by line. So we'll just let that finish. And you'll see it runs, it's in the background, it updates the grid, and everything's nice and flat and good quality data. So you select the lines, you run the algorithm. There's a small number of parameters to choose from. We'll touch on that in a couple of slides. We'll jump to the next benefit. It's physics-based. In this case, we'll start with the mathematics. So here's the image that we've shown on a few slides already. Really what's happening is the mathematical part that's doing the work is it's scanning through the point cloud and finding the neighbors to the port side and starboard side of a particular line and computing the RMS values in the areas of overlap. So in this case, on the left, you see where there's general good agreement, there's a low RMS value. Where there's general disagreement on the far right, you have a high RMS. And this is the signal that the algorithm is taking and it's trying to minimize. I'll show you an ugly equation. It's not that ugly, but it's probably the only equation we'll show in here. And this is what's happening. If you dig into the papers from Miriam and Tanaz and others, this is what they call the energy function. Is we compute the energy in terms of the RMS, and it's a function of the sound speed that's used to correct things, the depths of the various points, and then the overlap between the swaths. And you sum that, and you cycle through the search space, trying different sound speeds until you find a minimum. And that's the interesting bit, is the minimization of that function. The other part that's physics-based is the use of harmonic sound speed, and that's the output of the algorithm that, as we've implemented it, it computes the equivalent harmonic sound speed that's needed to get an equivalent ray trace location on the seafloor for the sound speed profile that's unknown. So there's a nice paper dating back to 1999 by Geng and Zielinski that kind of captures how it is that it's possible to do this. So this is a clip right from their paper showing two different sound speed profiles. And I've pulled a sentence out of that paper, and it's interesting. They say for two different sound speed profiles, the depth estimate difference related to the profiles, if they're different, is almost a function of only the relative area difference between the two profiles. And when the difference is 0 between the profiles, then quite typically the error in ray tracing result is 0. And so let's look at what that means practically. So we'll draw a green sound speed profile on the left, and we'll have the equivalent green ray trace on the right. And another sentence from the paper sums it up nicely here. I'll put it on here. I'm not going to read it out loud, but it says that if I took another sound speed profile, let's say in red, on average, the area difference between the red and the green is 0. If you remember your calculus integration classes, the integral between the red and the green functions is graphically drawn here to be about 0. What that means is I can take a very different path through the ocean, but I can land at the same spot. There's a family of sound speed profiles that can get me to the same spot with the same travel time and depression angle. And the harmonic sound speed is an extreme version of that. So if we had the green profile as the truth, the harmonic sound speed is what we typically use for single beam echo sounding travel time corrections. So the harmonic sound speed computed from the green profile, as long as we use the starting surface sound speed measurement and introduce an infinitesimally small layer where we can have one-time refraction kink of the original depression angle, you can land at the same spot with a single velocity sound speed profile. And this is what's going on behind the scenes that allows us to get away with using the harmonic sound speed as a replacement for an unknown sound speed profile. So the last benefit we want to cover is the algorithm's accountable. And what do we mean by that? If I look at the bottom right, you'll see the map again with the survey line going from A to B. And the outcome of the inversion from the algorithm is a harmonic sound speed profile. Sorry, a harmonic sound speed time series. What that means is as the vessel travels from A to B, if you look in the graph I just put on the screen, time is proceeding from 4:15 in the afternoon to 4:30. And the harmonic sound speed that the algorithm is outputting is preserved as a time series. And that's actually what's then used to correct the data in further processing. And as you change the parameters of the algorithm for the inversion, we won't get into the details of that. The outputs of each run are preserved as a different time series, with the last time series that you ran the last algorithm run always taking precedence. So you can explore different parameters. They're preserved, you can see them. And what's interesting is because this is treated as a time series and it's displayed in Qimera's time series editor, you can review that. You can clip out spikes. For example, in this case, you see that one result is quite smooth and the other's not. If you felt that the rougher, unsmooth one was better except for a few spikes, you could remove those spikes and it would be treated and used in the subsequent application. If you don't like the results at all, it's quite easy to back out entirely. And what I'll show you is that in this next slide. If you go to the processing settings editor under the sound velocity tab, you'll see on the bottom right, as of Qimera 1.6, there's a new section here that controls the use of these results. And you'll see there that there's a global override that says, do you want to use the results from this algorithm or not? That's the top tick box. If you had multiple runs from the same data set, they would collect in that prioritized list on the bottom. And you could disable a particular run result, or you can reprioritize them if you felt you had to. If you want to explore it and see if it makes the data better, it's quite painless to do it. That's just computing time. And if you don't like the result, you just come in here and you select all your files, you come into the processing settings editor, and you just disable the application, and it reverts back to whatever sound velocity strategy you had before. So it's quite easy to explore, it's quite painless, and it's very easy to get back out of it if you're just in the mood to see what it does. So we'll switch to the third phase of this webinar, which is talking about community acceptance. So I told you the horror story that I personally went through, and we were able to fix that data set. We've covered the algorithm, roughly how it works, some of the math behind it, and the benefits. And what I want to touch on now is how do we demonstrate that this actually does not destroy the fidelity of my data. And so what we've done, and this is part of the paper that's in one of the attachments that you'll see in the webinar, is test against a baseline data set that's of decent quality, or in fact even very high quality. And this is covered in the paper. What we'll do is show an example where we've got the sound speed profiles from a small data set collected in the Netherlands. Those are shown in gray on the left-hand side of this graph, and I think there's 4 of them there. And what we did as part of this work is we introduced a fake sound speed profile that's wildly different, and if you read off the scale on the graph, it mostly bumps up almost 15 to 20 meters per second, if not more. So this would be considered a large blunder application of a sound speed profile if you were actually on a survey. For example, you might have grabbed a profile from the previous job in a different part of the ocean or done a different season. So we're really stretching it to see how far we can make the data, which was in a good state when we got it, and see, let's make it purposely bad and then see if we can recover from it using the TU Delft algorithm. And that's what this image shows. This is an image straight from the paper that we worked on that supports this talk. On the left, you see a terrain model showing this, and this again is color-coded by the uncertainty of the soundings in the grid. So showing the raw data as processed with the raw sound speed profiles, and you see for the most part it's a nice light blue. There's good agreement between the multiple survey lines up and down through that area. The second tile shows what happens when we take that blue sound speed profile on the left and apply it to the data that was good out of the box. We've made it incredibly bad. And the evidence of that is the green and red stripes that you see up and down that are tracking the survey line, track line. And then finally, the result on the far right is what happens when we take the bad data that's at this point has completely forgotten about the original sound speed profiles and is in a very bad state, and we apply the TU Delft algorithm. And you can see that we really beat down the uncertainty between the successive adjacent passes to a very similar level to what we had in the first place. So those are some maps. It's interesting to tunnel a little deeper. And typically, let's just look at some slice results. So the black box that's running across the 3 sequences of images here, that's just highlighted in red. What we'll do is grab the soundings from there. So this shows what it looked like, the raw data out of the box as collected and processed with the raw sound speed profiles. And you can see there's generally quite good agreement between the different passes. In this next section, it's the same section, it's the same soundings. This is what they looked like after we've purposely introduced the false sound speed profile and made everything bad. You'll see that there's disagreement and kinks. I'll just move my mouse a little bit to point that out. There's disagreements of up to 50, almost 50 centimeters between the outer soundings of one line and the nadir soundings of the next. And you see that in a variety of spots. And then lastly, this is what the same set of soundings looks like when we repair the data. We bring it back to a better state with the TU Delft algorithm. And you can see there's very, very nice agreement between the different passes. And visually here, it's quite difficult to compare exactly the difference. So this is typically where people start to use some analytical tools like surface differencing. So what I'm showing here is a difference between the original grid that was processed with the raw sound speed profiles and then the grid that was repaired and recovered with the TU Delft algorithm. And we've used a polar color map where white indicates a 0 difference, blue indicates a small positive bias, and red indicates a small negative bias. And you can see for the most part it's white throughout with light blues and light reds. So this was done with the surface differencing tools in Qimera and also in Fledermaus. This is the typical result you'd see at the end of that run. What I've done is I've summarized what happens when I take the surface difference between the terrain model that was processed with the fake SVP versus the original one. And you can see that we did a lot of damage. We purposely introduced a 33 centimeter bias, both in the median and the mean, and the standard deviation through that was plus or minus 6 centimeters. The same statistics, once we repair the data and get it back to a good state and compare it to the original baseline, you can see that we're down to a 2 centimeter mean and median difference between the repaired data and the original baseline. And also the standard deviation goes down quite a bit. And what's interesting here is there's a dark blue and almost black ribbon indicating that there's a higher bias in the difference between our repaired data set and the original. And let's look at the uncertainty colored plots for the baseline data set and the one that's repaired with the TU Delft algorithm. And we'll focus right in on that area there. And I've just lit them up with a red circle with both. And you'll see on the baseline data set, now that we're looking more closely, you see a faint set of green ribbons running through there that indicate that there's not as great of agreement between the different survey passes as we had thought. And you can see that the TU Delft algorithm quite handily got rid of that. So there was a small refraction problem that we didn't even recognize when we first set out. So our baseline data set was not as great as we thought it was. So that's the end of that, and I'll just wrap up with a little bit of future work. This talk, like I said, was given originally at the Shallow Survey Conference in St. John's, Newfoundland a few months ago. So I'll leave the points in of the future work, and then we can touch back on what we've improved since then. So at that point, we said, what can we improve? There were some issues with dual head systems with minimal line overlap. And there are issues with suboptimal vertical positioning. This really relies on the only thing to have to fix being a refraction problem. If you mix that up and muddle it up with vertical referencing problems, it gets much more difficult to tease the two apart. What we'd like to do in the future is also better understand the sensitivity to things like the survey line spacing. Can I push this algorithm with a 15% overlap between my survey lines, or do I need at least 50? And that's the number that we don't quite have yet. We don't have access to a lot of data sets like that internally at QPS. But I'll touch on that in the next slide. We're curious about the sensitivity of the algorithm to seabed morphology. If you have lumpy, bumpy seafloor or flat and smooth, does the performance degrade with that at all? What about oceanographic conditions? When we first started showing this to people, I had one person say to me, "Oh, that'll never work in Australia. The water's hot there." And I said, "Okay, well that's an interesting thought. Well, we need to explore that. Is there something different about the physics of refraction that this algorithm couldn't cope with?" And until we really get a wide range of data sets, that's a tough question to answer. So touching back, what we've fixed since this slide was first shown a few months ago is we've dealt with the problem with the dual head systems with minimal line overlap. That was fixed in version 1.7.4, which shipped several weeks ago. And that also included a new parameter to allow you to constrain the results of the harmonic sound speed output to basically box it in a little bit to something that's reasonable to cover the range of oceanographic conditions. And this helps it find the right solution. Sometimes if you have interesting survey line geometries or overlap that kind of goes from 50% to 5% and back to 50 because you have free line running with the surveying, this helps box that in a little bit to constrain the algorithm. So that is what I'll move my mouse to point that out, is these two new parameters here. So I wanted to come back to this last point. The one thing that we get asked the most is, what's the line spacing that I need in order for this algorithm to run really, really well? People want to know, when is this going to break down so they can do good survey planning, so that they know that they can use this and it's there if they need it. So we don't have the answer. So this is where I think the user community comes in. We'll make this interesting for you. I'm doing a call out. I'm looking for someone who has a little bit of ship time, maybe about as long as it would take to run a patch test. We need 11 survey lines spaced at a half a water depth. So in 20 meters of water, we want 10 meter spacing. You have to have great vertical control. It's nice to have SVP casts immediately before and after. These are the file formats we're looking that work quite easily in Qimera that we can work with. And just get in touch with the sales team and put the subject TU Delft Challenge. We realize this is a cost to you to go out and collect this kind of data, so we want to make it interesting for you. If you have this kind of data set and it meets these criteria, and we haven't already had data sets submitted, we're willing to grant a free 1-year Qimera subscription with the TU Delft add-on as a way to thank you. This will help us come up with better guidelines for the community how to use this tool. So I think with that, we'll wrap it up. The summary. This is something that we're really proud of with QPS, is the way that we can partner with research institutions to bring really great technical ideas from the research domain to operational tools. And this is yet another example of that. There's a new tool now that's objective, it's automated, it's physics-based and accountable. And this is, I can't, of course, say who gave me this quote. It was one of our hardware partners who uses our software during shakedowns and installations. And they wrote me an email after we released this and said they just processed a client's data with the inversion algorithm, and poof, 95% of the refraction problems were gone. So we'll leave it there. I've seen the questions bubble popping up, so I think there's probably a nice little backlog of questions to get through that Sam may not have been able to answer. So we'll switch to Q&A mode.
There's actually, so a couple of the questions were just related to a screen issue. So that's some of the dialogue that was going back and forth. And then Doug Bergeson had said that he can confirm that the algorithm actually works in Australian tropical waters with the project that he had been working on.
That's excellent. We have one data point now.
Yes, and he also mentioned that, you know, for folks who are interested in Qimera, that they can also contact their local reseller if
yes,
needed.
Of course, yeah. Yep.
And then it does look like there's a hand raised, but I don't see a question right now. Here it's coming in right now. We got a couple questions coming in. So let's see. What's the effect of using this when there is very little overlap or when there is no overlap? Is the first question. So.
Okay, the easy one to answer is if there's no overlap, it just does not work. It will not give you a result. Error out of bounds kind of result. It uses the redundancy of the overlap to power the algorithm. And to touch back, I think the last slide, actually, if I just jump back to it, this is exactly the problem I'm looking to solve with a data set like this, is if I have 11 survey lines and they're spaced at half a water depth, I can run this through the algorithm and see how it works with wonderful, overly redundant collection. And what we can do is a little leave one out type analysis. You then drop every second line and then you get a result. And then you drop every third line and you get a result. Drop every fourth line until you get it down to what might be some people really pushing the edge with the outer beams of each line just touching. It will give you a result. What we want to come up with is a decay curve. And the confidence level, even just something like the uncertainty variance based on the line spacing. So that's exactly why I'm calling out for a data set like this, because we don't have an answer for that. And with the data sets we have in house, I don't feel confident that we'll get enough data to build up a decay curve.
So another great question here, do you foresee a future where mechanical measurement of sound velocity structure is completely obsolete?
I had almost this exact same question at the Shallow Survey Conference. And I said then, and I still say it now, until we know this works 100% all of the time in all scenarios, I don't think anybody in their right mind would jump in there and go out and not collect sound speed profiles until we know for sure. And it's going to take us a little while to build that up, that community knowledge and trust of something like this. It could happen. In the end, we've got a wonderful bit of mathematical machinery that flattens the data for us, and it seems to do it in an unbiased manner. We've got strong evidence that it works quite well. I think it'll be a little while before we're at a spot as a community to completely abandon the practice of sound speed profile measurement. It could happen, though. But it'll take us a little while to get there, and it's just getting over people's their uncertainties about the uncertainty that comes with using algorithms like this.
Great. And so another question, does this tool still work in highly dynamic oceanographic conditions where things have changed from one survey line to the next?
Yes, it's specifically designed for that. I've demonstrated as it's a one-click wonder, and it seems to grab all the data and compute it at once. What's actually happening is we chunk it up. One of the parameters in the algorithm is the, I can't recall the name for it. It's basically how many pings along track are used to solve for one instance of the sound speed for the center of that bundle of pings. And so let's say it's 100 pings along a survey line, and you grab the equivalent number of pings to the port and starboard lines, and you solve for the value. And it's the granularity of that window size that lets you resolve quickly varying oceanographic conditions. So it does, by design, is purposely built to handle that exact scenario. If we expose more of the parameters of the algorithm and let you choose something like a single harmonic sound speed per line, then that wouldn't handle that. But by design, it's chunking it up and proceeding through the data set like that. So naturally, the outcome is handling that. And if I go back a few slides, excuse the lag here between me punching slides and getting to, I think it's right here. This slide here shows the time series, and you look at the blue line, the smooth harmonic sound speed. You'll see from the beginning of the line, the algorithm is giving you a result of 1456 meters per second. I'll just move my mouse here. So right there, the blue dot, 1456 at point A, which is in the map over here. By the time we get to point B, it's dropped to 1451. And this is a 15-minute transect in Bedford Basin, and that's not very long. We were going quite slow. So you can see that there's a natural variation there that's being resolved, and you can see from the overall results that we've shown that it's resolving the differences in oceanography over such a small transect like that.
Great. So another question is, once the tool is run, does it create an SVP that can be exported and compared to the original SVP collected during the project?
No, it doesn't. The closest to that is the graph that I've got right up here. As you can see that, I think one of the slides I showed the mathematics behind the reason that we can get away with using a single sound speed instead of an entire sound speed profile. The result that comes out is this single sound speed, the harmonic sound speed. And so that value could be compared to the harmonic sound speed of the original sound speed casts. That's not something we have a capability to do in the interface right now. We do have some code that we haven't actually switched on that allows you to compute the harmonic sound speed of any given sound speed profile. So I think that's within reach. If that was a desirable QA step that people would like to be able to do to prove that this didn't wander too far from the original sound speed conditions, that'd be something that we could add to the interface, basically to give people more confidence, and then to also be able to pass on the data set to an end user to say, I use this algorithm and these are the results and I'm confident and I can show you that I am. So that's a really good point. If you don't mind capturing the name of that person, I wouldn't mind maybe have a follow-up with that.
Great, yeah, I will do. And then somewhat related is, how does the tool become tied into the TPU results?
The TPU results are unaffected by this. We allow you to have the sound speed uncertainty measurements. If in the sound speed editor you can specify the uncertainty of the sound speed sensors itself, and that's still natively used. That's I think an area of research. I think the gut feel is the data got better, so the TPU must go down. Numerically, I'm not sure that if you have refraction problems that people actually have TPU beforehand that captures the nature or the additional uncertainty due to the refraction problem in the first place. So it's an interesting problem to solve from a research point of view. And I'm not sure anybody's actually really got a good handle on how to solve that. There's been a few ideas that I've looked at in my research career before this, but there's certainly some room for some work there.
Great, and then last question here. It says the scenario is there's a bad weather survey conditions, and the TVG parameters changed, which led to edge beams being deformed. So can TU Delft help with that problem? So in that particular situation, there was SVP and TVG problems.
If the TVG problems made an artifact in the bathymetry that looked like a refraction problem, this refraction problem removal machine will certainly try to get that out of there. That's a really interesting question. It might just work. It would have to strongly mimic the nature of a refraction problem. I'd be interested to see the results of that.
Good. And so I guess that's a nice reminder for anybody who is interested in possibly evaluating the software. If you type evaluate into the chat box, I'd be happy to follow up with you through email and help get you an evaluation so that you can actually try this tool out with your data yourselves. And then, of course, be able to ask additional questions. We can follow up with those in email as well.
And I'll add the point that if you're an existing Qimera user and you don't yet have this add-on, you can certainly evaluate the add-on itself. That is something that we can make happen. If you've not used the software at all before and you're interested in the software and the add-on, we can accommodate that too.
And last question, there is one more. It got hidden there for me for a second. Will the correction affect backscatter values?
It depends on where you're going to process your backscatter data. I'll answer from our point of view with QPS workflows. So if you went to Fledermaus Geocoder Toolbox, also known as FMGT, the GSF files that we create would have better georeferencing. So the sounding footprint for each beam would be in a better spot. The depth values don't typically have much to do in isolation without the context of surrounding depth values. They don't really influence the backscatter correction that much. Where it would improve things is if you were doing a terrain model correction to improve the insonified area portion of the backscatter corrections. You would see an improvement. I don't think it would be very much. In fact, I'd be guessing that it would be hardly noticeable at all. Backscatter just isn't as sensitive to this type of artifact as obviously the bathymetric results are.
All right, well, I think we have actually captured everyone's questions either directly in the chat box or verbally.
Great, okay.
All right, well, thanks for joining us, everyone. And I'll follow up with an email that will also contain the YouTube link, so that way if you want to view the webinar again, you'll have the opportunity to do that.
Thanks, everyone, for joining us.
Bye.